Due to physical and spatial limitations associated with passenger and light-duty vehicles, the energy delivery methods have practical limitations. The most popular means of energy to date has been stored chemical energy to mechanical kinetic energy through the burning of fossil fuels in internal combustion engines. Looking to the future, alternate forms of energy will be required that are more sustainable in how they are collected and processed, or a change in how traditional fuels are used to power vehicles with evolving engine technology. Yet, these alternate forms of energy will still need to be compact and energy-dense enough to support a reasonable range between fill-ups and affordable enough to maintain the modern standards of mobility. The same applies to emerging engine technologies. The solutions need to meet the demands of today and be future-proof. The concept of internal combustion engines has been around for many, many years. However, people experimented with different styles of engines. As you may know, the most common engines nowadays are V-type and inline. You may also know of the rotary or boxer engine. These all accomplish the same goal while functioning in different ways. One of the many engine concepts was called the opposed piston engine. They were first tested in the late 1800s and saw some usage during the 1900s for naval, military, and industrial uses. An opposed piston engine has two pistons facing one another that share one cylinder. These engines do not require engine headers, and because they are diesel engines, they do not need spark plugs either. With two pistons, each cylinder can reach a higher compression ratio than their one piston to one cylinder counterparts. Higher compression ratios contribute to a higher efficiency and better fuel burn. Efficiency is one of the most important aspects of an engine and ties into thermodynamics heavily. The second law introduces the concept of entropy, emphasizing irreversibilities in processes. Engine efficiency is vital for energy conservation and environmental sustainability, guiding efforts to optimize engines for reduced fuel consumption and emissions. In essence, engine efficiency in thermodynamics provides a crucial framework for understanding and improving the performance of heat engines in various applications. With higher efficiency, there is lower power loss and consumption. Fuel becomes more efficient and capable of providing power. Take a look at the animation. You can see there are 4 pistons and 2 cylinders. This concept shows similarity to the boxer-style engine. A company called HTS Power has been specializing in opposed piston engines since their founding in 2004. They worked to make a more fuel-efficient opposed piston, two-stroke engine that meets today's stringent emissions standards. Their engine style resembled that of an inline engine. In 2015, their research and development results gained the attention of the United States Army and of the United States Department of Energy. The Army was interested in tanks, and the Department of Energy was interested in development of an opposed piston gasoline compression ignition engine. There are other awards and grants they have received to support their efforts to develop an engine with improved efficiency. Research they do has continued to this day, and their information can be found online. An emerging fuel technology is in the reuse of other byproducts or the processing of renewable crops to produce green biofuels. The renewable nature of the production and processing of plant-based fuels has the potential to solve many of the limitations of traditional fossil fuels. Which bio-based fuel will be the most effective is a matter that there is less certainty. To determine which fuels will be the most effective, the efficiency of the fuel needs to be analyzed from a holistic point of view. Naturally, the efficiency of the fuel within an internal combustion engine is a concern for the end user. Additionally, The efficiency of the manufacturing and refining process is critical to the long-term success of bio-based fuels. To evaluate the overall efficiency of biofuel, the energy inputs through the system are compared against the potential chemical energy of the fuel with the efficiency of the internal combustion engine using the biofuel factored. Since each step along the production uses energy, a holistic view called biomass to wheel is needed. Using this framework, various biofuels can be compared to evaluate the pros and cons of each. Some sources of biofuels are vegetable and seed oils, plant biomass like trees and grasses, and algae. There are both economic and thermodynamic pros and cons to each type. Thermodynamically, algae has an advantage as the nature of the plant's structure, the absorbed energy, is predominantly converted to biomass that is usable for the production of fuels. This combined with the quick growing rate of algae can result in yields of 10 times that of other plants used in biofuels. Current studies in the use of algae for biofuels are looking at how to make the overall process more efficient. Much of the energy inputs for algae are in the harvesting and refining processes. Current production technologies range in efficiency from 39% to 57%. The efficiency of biofuel production is only part of the equation for biomass to wheel consideration. Other factors include distribution efficiency, which would ideally be similar to the current fossil fuel distribution network and have no net negative impact on biomass to wheel. The other major consideration is the combustion efficiency of the biofuels in internal combustion engines, most commonly in diesel engines. The efficiency of biofuel combustion is also important due to externalities such as chemical and particulate pollution that can have negative effects on the environment and population health. Studies have shown that blending traditional diesel fuels with biofuels or biogases can have positive effects. For instance, blending biogas with traditional diesel fuel resulted in a reduction of nitric oxide by over 25%. Using a very different fuel blend, minimal change in carbon emissions was recorded when blending plant-based fuel with natural gas, thus combining the benefits of both production processes. This mixture also can significantly reduce the volume of particulates emitted due to incomplete combustion. If just plant-based fuels are combined with plant-based gases, a 30% plus reduction in nitric oxide can be achieved. This is again in addition to the sustainability benefits from solely plant-based fuels. The biggest limitation of biodiesel in commercial use is the lack of detailed research on optimizing the engine tuning for running on biodiesel. The differences in octane rating and chemical and physical properties limit the effectiveness of off-the-shelf diesel engines. There is some research being done, however. Much of it is protected by proprietary processes meant to market the technology to a specific segment of the industry. This more tailored approach doesn't aid in the more widespread adoption of biofuels. The future of the use of biodiesel will rely on the development of diesel engines specifically for the clean and efficient use of green renewable fuels. This technology, combined with advancing diesel engines for fossil fuels, has the potential to cross paths and make serious gains for clean energy. An opposed piston diesel engine powered by biodiesel may be a marketable solution. Will it happen? We sure hope so. These are our sources. Thank you for watching.